Welcome to a new lesson of heat transfer. Today we're talking about the heat conduction equation. First, we need to remind ourselves that temperature is a scalar, whereas heat transfer is a vector. So to define heat transfer, we need to define the magnitude of heat transfer and the direction. So it's important to define a coordinate system to study problems in heat transfer. So once we have defined a coordinate system, so we have defined a coordinate x that, for example, in these cases runs from left to right. We note that the heat transfer Qx is positive if it's directed toward the x growing. So in this case, x is going from left to right, and Qx is flowing from left to right, so Qx is defined as positive. In this case, x is still running from left to right, but Qx is flowing from the right to the left. So in this case, Qx will have a negative value. In our problems, sometimes we are given the temperature distribution in space. So we're given Tx and we want to find the vector Q at every point. In other cases, instead, we're given the heat transfer, the vector heat transfer in space, and we want to find the temperature distribution. Sometimes we will use a Cartesian system where T is a function of x, y, z, or we will encounter a problem in cylindrical coordinates or in spherical coordinates. It is now important to define some terms. We'll define a problem to be steady when the heat transfer and so the temperature do not change over time. Whereas we define a transient problem or unsteady problem where instead there is a change over time. So for example, if you imagine a hot cup of coffee on a table and we leave it there for a few minutes, then eventually the coffee will cool down because heat flows from the cup of coffee, the hot cup of coffee, to the environment, in this case a cold room. So this is an unsteady problem because the temperature changes over time. In real life, of course, we have three-dimensional heat transfer problems, but often in heat transfer engineering, we can simplify the problem as a 2D problem or even a 1D problem. We'll have a 2D problem if the temperature does not vary very much in one direction, or 1D problem when the temperature does not vary much in two directions. So let's take a case we saw before with a thin wall. In this case, since the wall is very thin, heat will usually flow mostly along the x direction and will not flow much along the y direction. Because in this case, in the wall normal, in the vertical case here, y, the temperature gradient will be quite small. And Qx and Qy, in this case, will be also much larger than Qz. So in this case, the one-dimensional approximation is valid. So we have seen before the Fourier's law in one dimension. So Qx is equal to minus k dt dx times a. But in 3D, we can generalize this, and we have the vector q equal minus k gradient of t times a, where the gradient of t is the temperature gradient. It's a vector, and the component are the partial derivatives of t with respect to x, then of t with respect to y, and t with respect to z. This is, of course, in the Cartesian case. So in the three-dimensional case, Q has three components, Qx, Qy, and Qz. So we can split each component, and each component has a value proportional to the partial derivatives with respect to that direction. And we note that we need to have here the partial derivative sign because the temperature depends on x, y, z in this problem, and maybe also over time, on time. So we need to use a partial derivative sign. In our problems, we will also find cases with heat generation. So what do we mean by heat generation? In a medium, often we may have a conversion of heat. So we can have electrical energy, nuclear energy, chemical energy that's translated into heat. So we have a change of energy, type of energy, and we say that thermal energy in this case is generated. We can have usually a heat source in the problem. So for example, we may have an exothermic chemical reaction, or we could have a heat sink. In this case, we would have an endothermic reaction, where the energy goes from thermal into the chemical bonds. Usually when we have a heat source or heat sink, we have a volumetric problem. So we indicate this heat generation as a small e dot, and that's in watts per meter cubed. So this is a local heat generation. And to find the heat generation everywhere, we will have to integrate this value, this quantity, over the volume. Let's look now at the heat conduction equation. And of course, we start from a conservation of energy. Let's consider first the case of Cartesian geometry. So we have here part of our thin wall. We define a position x and a further position x plus delta x. So the distance between these 2 points is delta x. And in this control volume, we have a Qx that enters the control volume from the left, and we have a Qx plus delta x leaving the control volume. So we can write the first law of thermodynamics, that is the conservation of energy. In this case, we have Qx minus Qx plus delta x, plus some heat generation may occur inside the volume. That's equal to delta E divided by delta T. So the change of energy, thermal energy within the system. So let's look at delta E and the heat generation now. So delta E, as I said, is the change of thermal energy. So this will be the mass times the specific heat times difference in temperature at T plus delta T minus T at T. So that's a temperature at the time T plus delta T and the temperature at time T. If we write now the mass as the density times the volume, A times delta X, then we have a further expression for the thermal energy, or better, the change of thermal energy of the system. And the heat generation is now the local heat generation times A times delta X. So we can substitute this in the previous equation, and we find an expression. So I see you next time, and we'll continue with the derivation of the heat conduction equation. Thank you very much.